deep learning has benefited from high-performance CPU-GPU systems and why we consider highly integrated 3D heterogeneous systems to improve their performance. Then I'll discuss what are the design issues that we face when using these 3D heterogeneous systems for CNNs. Then we'll talk about how to design the objectives for these 3D heterogeneous systems in order to address the design issues that we saw in the motivation. And then we use the multi-objective optimization, MOSA, to solve for these objectives in a joint manner. So very similar to the last talk, actually. Then we'll go over the experimental results. We'll discuss the benefits of this multi-objective optimization, the NOC characteristics, and the full system characteristics. So we've all seen that deep learning has made huge strides in many different types of domains. So we've seen in speech processing, computer vision, natural language processing, complex decision making. And one of the main characteristics that these deep learning applications are very data intensive. And we're able to utilize the GPU's data parallelisms in order to enable large computation and large data sets. And we've seen that many common systems utilize these GPUs. So for example, desktops use CPUs plus external GPUs. Servers use clusters where you have CPUs and multiple GPUs. And other architectures that use CPUs plus another type of accelerators like the Google GPUs that are very good at these types of applications. But the problem with all of these systems is that you have a costly delay and slash energy interface between the CPU and the GPU. And so the solution, what is the solution for that? So in recent years, what we've seen is that by putting the CPU and the GPU together and increasing integration, creating these heterogeneous CPU-GPU systems, we're able to enable a higher data compute at a lower power. And industry has made systems with increasing integration, starting from back in 2010 with the Intel HD graphics into the NVIDIA Tegra K1 with 192 GPUs, and then finally this year sometime with 512 GPUs on the NVIDIA Tegra Xavier. So what's next? So what we think is next is going to be integrating this all into a 3D heterogeneous architecture. And we're going to look into how to accelerate these, or how to design these 3D heterogeneous architectures in order to accelerate CNNs. So here's an example of a 3D heterogeneous architecture where you have multiple planes, and each plane has multiple dies, or multiple tiles. And in this case, we have a system with 2 layers and a 3x3 tile configuration. And these tiles can be CPUs, GPUs, or memory controllers. And these memory controllers are the ones that hold the last level cache and the access to main memory. But using this, we faced 2 problems. One was that we saw a lot of NOC congestion. We saw that certain links within the system were being heavily utilized. And the second problem is that there were a lot of thermal hotspots. We'll talk about later how we got to these configurations and experimental results. But these were some of the problems we faced and we're trying to address in this paper. So in order to try to solve these problems, what we should do is that we should design a network in order to mitigate this NOC congestion and to place tiles intelligently so that we reduce the power density and reduce the thermal hotspots. So it's very clear where the thermal hotspots coming from. 3D integration, you have higher power densities and therefore higher thermal hotspots. But to understand where the NOC congestion is coming from, we examine what is the traffic characteristics of these CNN training applications. So here we look at 2 different CNN applications. We looked at CFAR, which is a image classification into 10 different objects. We use one of the basic content CNNs. And then we look at MNIST, which is classifying handwritten digits into digits 0 to 9. For anyone interested, we have the configuration of the CNNs that we used here. And basically what we do is that we take the data and we use the basic forward pass, backward pass, and then we examine what are the traffic characteristics for each of the layers of computation. So for each convolution layer, for each pooling layer, what are the traffic characteristics? And from what we've seen, that we aggregated the traffic characteristics into 2 different categories. One is the memory controller to core, CPU or GPU, and vice versa, back and forth, and the CPU to CPU GPU to CPU GPU communication. So either the above. And what we saw was that a lot of the traffic was dominated by the memory controller to core communication throughout all the layers of the application. For all the layers, it's above 75% of the total traffic seen on the chip. And what happens is that since memory controllers themselves are a much lower in count than the actual computational cores, we see these many to few and few to many traffic patterns. And what happens is that these memory controllers tend to be the traffic hotspots and the location of the congestion we saw earlier. So when we create the NOC, we should definitely consider these types of traffic characteristics and try to mitigate these problems. For example, if we just use a simple 3D mesh, what happens is that links near the MCs tend to be heavily utilized due to these traffic patterns. And what we should try to do is to add more path diversity in order to allow these links to be helped to alleviate these congestion.